Swayam Prabha. Digital India. Educated India.
Okay, tell me if it's a repeat. Did I talk about Hermitian matrices? No, okay. Did I talk about orthogonal matrices? I thought I did. Cos theta, sin theta matrix, and some other examples of orthogonal matrices. Okay, orthogonal matrices. This you already have been involved. And unitary matrices? No. No. Okay. These two are extremely important in chemistry, physics, in the formulation of quantum mechanics using matrix methods. These two are fundamentally important. And the mechanics, quantum mechanics, which was discovered to begin with, the old quantum theory was discovered in 1900 by Max Planck. And then 1925, when Heisenberg, Max Born, and his colleague Jordan came up with the mechanics of, the new mechanics called the matrix mechanics for describing the spectra of atoms. And later Schrodinger followed that up with his own fundamental equation called the Schrodinger equation. Okay? Now, the matrix mechanics, which is quite often used these days in computational chemistry and in computational physics, the matrix mechanics, these are fundamentally important, and also associated with the Hermitian matrices, there are quantities called eigenvalues and eigenvectors. These are today the norm of whatever we know in mechanics and the chemistry, the electronic energy levels of the atoms and molecules, the nuclear, that is the atomic energy levels, then you have the molecular energy levels due to electrons, and also due to other molecular motion like the overall rotation of the molecule that contributes to the total energy of the molecule. The atoms in the molecule also vibrate about equilibrium, about their equilibrium bond. And these vibrational motions also are connected with what are called the normal modes or vibrational modes. And the eigenvalues are fundamental to understanding the vibrational frequencies. Then we have the electronic motion. Then we have the nuclear, the magnetic moments. Nuclei, most nuclei have a magnetic spin quantum number, and the quantum number for the nuclei are not limited to the plus half or 1/2 as it is in the case of electrons. Electron spin is limited to the quantum number half and two states of plus a half and the minus a half, what we call as the up spin and the down spin. The nuclear magnetic moments are not limited to those two. Nuclei can have quantum numbers greater than half. Most familiar example is deuterium. The spin quantum number for the deuterium nucleus is 1, is not 1/2. And then there are many other nuclei. Chlorine, for example, the most common isotope of chlorine, chlorine 35. The quantum number, magnetic quantum number for chlorine nucleus is 3/2, not 1/2. Iodine, an isotope of iodine has a quantum number 5/2. Okay? So magnetic spin quantum numbers and the magnetic moments of the nuclei are useful in understanding the magnetic properties and what you see in the nuclear magnetic resonance, which is one of the most important spectroscopic methods, okay? What you see as MRI when you go, I mean, if you ever have to go to the hospital and take a scan, the magnetic resonance imaging has fundamentally rooted in the properties of the magnetic moments of the nuclei. And in the presence of external magnetic fields, these nuclei create additional energy levels due to the magnetic quantum number. And controlling them and playing with those magnetic energy levels leads to entirely the whole new spectroscopy known as the magnetic resonance spectroscopy. Okay? So eigenvalues are everywhere. Okay? In chemistry, pretty much also to understand the dynamics, the chemical dynamics of molecules undergoing at the elementary level, if we have to look at what is a molecule interacting with the other molecule, how does it do? And how does a reaction take place? To do that, one must study the mechanisms of these chemical reactions. And then when you study these mechanisms, sometimes you come out with the elementary reaction steps. And these elementary reaction steps, the dynamics of that is also controlled by the corresponding eigenvalues. But all of these are associated with a quantity called the total energy of the system, which is known as the Hamiltonian. Okay? Total energy, which is the sum of kinetic energy, energy due to motion, and the potential energy, which is energy due to position. Position, okay? So the sum of the two is known as the Hamiltonian, and there are states of the Hamiltonian for a molecular system, for the atomic system, for any quantum system. There are states. The Hamiltonian is an operator acting on some state, and if that state is properly chosen, that state has the property that the operation of the Hamiltonian on that state gives you the state back except for a constant. Okay? This is a constant. Meaning Hamiltonian depends on, you see, kinetic energy and therefore depends on the momenta of the atoms. And the potential energy due to position depends on the coordinates of the atoms, the difference between the coordinates, because after all these are all Coulombic energies. You know, there is a nucleus which has a plus charge, there is the electron which has a negative charge. So if you start with some geometry, then the difference between the electron and the nuclei distances contribute to the Coulombic potential. So those are positional coordinates. Therefore, the Hamiltonian is a function of both position and momenta of all the particles, coordinates and momentum coordinates of all particles in the system. Okay? So E does not depend on any of them. E is a constant. Okay? It's a constant, but please remember the Hamiltonian is energy. It's a sum of the potential and kinetic energies. Therefore, the dimension of the Hamiltonian is energy, ml squared t to the minus 2. This is also dimensionally energy, but it's a number. Okay? And the example for that is the most famous one when you talk with the hydrogen atom. The energy level, what we call as the 1s energy level, is an example of the eigenvalue for the Hamiltonian, one specific eigenvalue. If you have the states 2s and 2p, there are 3 of them. Okay. All of them have the same energy, but this is E2, this is E1, and E1 is not equal to not equal to E2. It's a different energy. That is also a solution of the Hamiltonian for the hydrogen atom, giving you an eigenfunction. The eigenfunction is labeled by these. 1s is the eigenfunction. 2s and 2p3, these are 4 eigenfunctions. All of them have the same energy, E2. So in general, you have many eigenfunctions and many eigenvalues. Okay? So eigenvalues are fundamentally important even from the very beginning of quantum mechanics, that is when you studied the hydrogen atom, and later helium atom and all the other higher atoms. The periodic table, we have studied 92 elements. There are many more, okay? 118. Yeah, a lot of them are quite unstable, of course. So if you want to study in detail the energy level structure of these atoms, the electronic energy level structure, because you are only looking at what are the energy levels. When you say that 1s and 2s and 3s, etc., these are the electrons' energies. And so in helium, there are 2 electrons. So the electrons, in addition to interacting with the nucleus, they also interact among themselves because there is a repulsion energy between them. So helium atom also comes up. When you solve this Hamiltonian, you come up with energy levels. And the approximate model is that helium atom also has 1s energy levels, except that it has 2 electrons. Now, how do we place these 2 electrons? Can we put them all in the same orbital, same 1s orbital? This is called the orbital, or the wave functions. Okay? They are also wave functions. What are they? They are these. Okay? Wave functions, okay? Eigenfunctions. So eigenvalues and eigenfunctions are fundamentally important in the understanding of the energy level structure of the atoms. And even more, the whole process of chemistry is not to stop with the physics of the atomic energy level, but to understand why bonding takes place, why a molecule dissociates, and why there is a chemical reaction. Chemistry is about transformation of atoms, not about the static study of the energies of the atoms and energies of systems. Chemistry is completely about transformations. Therefore, why does a molecule form? So if you want to look at the molecular energies, of course, they are also eigenvalues of the molecular Hamiltonian. See, for example, hydrogen molecule, there are 2 hydrogen nuclei and there are 2 electrons. The question is, electron 1 is not with hydrogen 1, electron 2 is not with hydrogen 2 in the molecule. You can't distinguish them where they are. And you can only see where the electronic state probabilities are. And the probabilities are given by the corresponding square of the eigenfunctions in quantum mechanics. Absolute square of the eigenfunctions, not by the functions. So important is these eigenvalues are fundamental to all of chemistry and all of physics if you want to study them using quantum mechanics, because you want to understand what they do in their interactions with each other. So we will just see a simple example of the eigenvalues and eigenvectors for, as always the case, simple models. And the job of a teacher is to explain the simple problem on the board very well and give the more difficult problems for you to solve in your home, okay? So I would just do that. Okay? We'll start with a simple matrix. Hamiltonian, when I say it's an operator, Hamiltonian is a matrix. And the wave function that you see, psi, that is also a matrix, except that Hamiltonian is a square matrix, the psi is a column vector. Okay? Can you imagine that? For example, I write A11, A12, A21, A22. I have been given a matrix like this with 4 numbers. This can represent a 2 by 2 Hamiltonian. if you think about the spin of the electron has two possible states. Therefore, when you study the spin in general, the angular momentum is represented by 2 by 2 matrices for the spin angular momentum. Okay, so it can be a 2 by 2. Therefore, what is meant by an eigenvalue for this matrix is that if you call this as the matrix A, you write another vector X such that it has two components, and what is this? How do we solve for E? Okay, this is called the eigenvalue, eigenvector problem, and you can see that immediately the analogy is that this is the Hamiltonian equivalent, this is the psi equivalent, this is the E equivalent, this is the psi equivalent, isn't it? This is psi, this is psi. So this is the simplest case. Okay. Now, how do we solve this problem? Obviously, we have to solve from what we know. What we know is how to multiply matrices right now. Okay, so let's multiply the matrices. So what do you get? A11 x1 plus A12 x2 is the product of the two matrices, and this is what? The second one is A21 x1 plus A22 x2. This is the left-hand side, right? What is the right-hand side? Since E is multiplying the matrices, the column EX1 and EX2. This is the right-hand side. Okay. Obviously, when two matrices are equal, what does it mean? Element by element, they are equal. Corresponding element, an element in one matrix and the corresponding same row and column element of the other matrix should be the same. Therefore, you get the answer that A11 x1 plus A12 x2 is equal to EX1, and A21 x1 plus A22 x2 is EX2. Okay? And you can immediately write this as A11 minus EX1 plus A12 x2 is 0. Bring the EX1 on the side. And do the same thing here. Plus A22 minus EX2 is 0. Okay? Right? So everything is okay till now? Now, these are two homogeneous equations. In x1 and x2, these are the variables. Why is it called the homogeneous equation? Right-hand side is 0. Okay? There are no constants. There are no constants, free constants in the system. So what is the solution for the homogeneous equation? What is the requirement for a solution? If I have two homogeneous equations in two variables, what is the requirement? The requirement is, when you study it, you will see that the determinant of the coefficients should be 0. Okay? The coefficients are these, and these are the variables. x1 and x2 are the variables. So the coefficient of the determinant, which is A11 minus E, A12, A21, A22 minus E, that determinant should be 0. Otherwise, this doesn't have a solution. Example, 4x1 plus 5x2 is 0. Okay? Then suppose x1 and x2 were to satisfy x1 plus 2x2 is also 0. Does this have a solution? What is the solution for this? They both have to be 0. Trivial solution, because you see the coefficient 4x, x1 is equal to minus 2x2. okay? If x1 is minus 2x2, then 4x1 is what? Minus 8x2 plus 5x2, which is minus 3x2 is equal to 0. Therefore, x2 is 0. Therefore, x1 is 0. The reason is because the coefficient 4, 5, 1, 2 determinant is not 0. What is the determinant of this? 4 into 5, 4 into 2, minus 1 into 5. Determinants are calculated like that. You have to take the element and everything that is not in the same row and not in the column, you multiply by that. Likewise, you do that. This is the fundamental linear algebra for that. So, when will this be 0? This will be 0, suppose if I write 8x1 plus 10x2, if I do that, obviously you see that the first one is the same as the second one except by multiply by 2. But the determinant will be 0. The reason is one column is the product of another column. It goes to 0 automatically. Point is, on these two variables, if the determinant is 0, then we have a non-trivial solution. The solution is non-trivial. The trivial solution is variables x1 is 0, x2 is equal to 0. Okay? Now you write the solution. What is the determinant? Determinant is A11 minus E, A22 minus E. What's the next one? Minus A12, A21 is 0. Okay? So this is a quadratic equation in E. You see the product is E square minus E times A11 plus A22 plus A11, A22, that's all of that. And then you have minus A21, A12 is 0. Okay? Right? So what's the solution for the E? You know the quadratic solution. E is equal to ax square, ae square plus be plus c is equal to 0. What is E? What's the first term? Minus 2b, isn't it? Therefore, A11 plus minus b plus or minus, and then 2a, 2. A is 1 here. Okay. Then you have plus or minus square root of, there is a 1 by 2 because of the a, b square minus 4ac. So this square minus 4 times that. So A11 plus A22 whole square minus 4 A11 A22 minus A21 A12. Okay, that's a solution. Okay, but this is simplified. What is the simplification? This is A11 plus A22 whole square minus 4 A11 A22. So what is that? That will be obviously A11 minus A22 whole square. Okay, so the answer is E is A11 plus A22 by 2 plus or minus 1 by 2 square root of A11 minus A22 whole square plus 4 A12 A21. Minus 4 into minus, so it's plus 4. Okay. So we started with which matrix? A11, A12, A21 and A22. So now we found out 2 eigenvalues E for this matrix. Plus or minus. Therefore, plus is one eigenvalue, minus is the other eigenvalue. Okay. Now, suppose these two were 0. What are the eigenvalues? From there. Suppose these two were 0. This is 0. In fact, any one of them needs to be 0. It doesn't have to be both of them to be 0. Any one of them is 0, is enough. Because you take the plus minus combination of the square root of the square. Okay? Therefore, plus gives you A11 if A12 or A21 is 0, then E is A11, A22. For a diagonal matrix or a semi-diagonal matrix like that, the eigenvalues are the diagonal elements themselves. If both of them are 0, I would put it at AND, because generally when we do this for 3, 4, 5 dimensions, it's important to have all the diagonal elements to be off diagonal elements to be 0 for the eigenvalues to be the diagonal elements. Okay. Otherwise, you have these two. So, exercise. I've given you this. Find out the eigenvalues. I'm giving you 5 minutes. That's all you have. Now, please go ahead, all of you. Sorry? Why? If the off diagonal elements of the matrix, if they are 0, then you don't need to work hard for the eigenvalues. They are just the diagonal elements. Okay? You do the determinant, A11 minus E, everything else is 0. Then you have along the diagonal A22 minus E. So your polynomial equation, determinant equation is a product of all of them. They're already factored out. So E is A11, E is A22, E is A33, that's it. Okay. So, yeah. 1 and? What is the answer? Plus or minus 1, yes. For this, right? What are the eigenvalues? Plus or minus 1, yes. That's easy to find out, okay? Now, E1 is the plus, okay? Another question. E1 is A11 plus A22 by 2 plus square root of whatever. E2 is A11 plus A22 by 2 minus square root of this, okay? Therefore, what is E1 plus E2? A11 plus A22, okay. What is E1, E2? That's a little trickier. What is? Yeah, give me the final answer. What is E1, E2? A11, A22 minus A12. What is this? What is that? That's a determinant of A. This one, it's a determinant of A. What is this? This is called the trace of A. The trace is the sum of eigenvalues, okay? Trace. Sum of eigenvalues. Sum of diagonal elements, sorry, not eigenvalues, sum of diagonal elements of any matrix. Any matrix. Of any matrix, okay? So you have these eigenvalues. Now the question is, yeah, I know we are not going to do the eigenvectors today. The next slot when I have, I'll start from wherever I left, okay? So that you will have to remember it. But now, the two important properties of the eigenvalues are, they are called proper. Eigen is a German word, okay? They are called proper or characteristic. Why are they important? They are important because if they are eigenvalues of Hermitian matrices associated with quantum mechanics, they are the only things that we can measure experimentally. Okay? Hermitian matrices, we will sometime later, we'll see has only real eigenvalues. There are no complex eigenvalues. And Hermitian matrices represent quantities that can be experimentally measured. Position is a Hermitian operator. Momentum of a particle is a Hermitian operator. Angular momentum of a particle is a Hermitian operator. Kinetic energy is a Hermitian operator. We'll see what Hermitian is in the next definition, next class. Yeah. Come again? We are only talking about square matrices. Eigenvalues that we can write down, we are only limiting to square matrices. We are not talking about anything for a non-square. Rectangular matrices don't have these things. Okay? You have to generalize them by doing something special, and then you have to calculate what are called quote unquote eigenvalues, but we don't do that. For almost all the problems that we do on a day-to-day basis in quantum engineering everywhere, we deal with square matrices. So if it's an n by n matrix, it has n eigenvalues. But if it's not a Hermitian matrix, we'll see later that some of its eigenvalues can be complex. If it's complex, then there is difficulty in understanding what is measurable. A complex number is something that we cannot associate with a measurement, unless you say the square of the absolute square of the complex number, which is the square of the length of the complex vector. So there are special cases. So the point of having Hermitian matrices in quantum mechanics is that they all refer to real, measurable, experimentally measurable, associated with quantum mechanics, associated with the systems, okay, properties. So now I leave you, since the time is up, I leave you with a matrix which is like this. I is square root of minus 1. Square root of minus 1. Okay? Can you tell me? I think you don't need much time. What is the eigenvalue? In fact, from these two properties, you can immediately tell what that should be. Sorry? Plus or minus 1. Again, even though the matrix seems to have complex entries, imaginary entries, okay? The reason is, suppose you have a matrix A, which is A11, A12, A21, A22. We define Hermitian adjoint of any matrix A as if A is Aij, elements Aij, you can see that 1, 1, 1, 2, I is 1, J is 1 and 2. You can see this is 1 and 2, 1, 1, 2, 1. So Aij, I refers to the row number, J refers to the column number. A dagger is defined as Aj star, complex conjugate. Okay? The definition of A dagger is the transpose, Ij becomes Ji, transpose, and complex conjugate. When is a matrix Hermitian? When A is equal to A dagger, then we say A is Hermitian. Sorry? Complex conjugate of I is what? Minus I, right? Star, you do the complex conjugation. It's a complex number. Any complex number, if you say x plus iy, what is the conjugate of x minus iy? So that's what it is. Okay? So suppose A11 is x plus iy. Sorry, A21. A21 x plus iy. A12 should be x minus iy. That's what this is. Okay? Is this Hermitian? Is that Hermitian? No. Why? If this is A, what is A dagger? You have to take this row and make it the column. 0, I, and then this row minus I, 0, But please remember, you have to complex conjugate every element. Okay? So what is that? I becomes what? And minus I becomes what? So do we have doubts? Is it Hermitian? Yes? Doubtful. It is Hermitian. It is Hermitian. No, you don't need to. Okay? Yeah, I'm almost done. Yeah. So we'll continue. These are all small mathematical tools. See, my job is that you will listen to a lot of things from many others, but there are underlying mathematical tools, small things. Particularly, matrices are very important whenever and wherever you go after this schooling system for higher studies. Yes. They are Hermitian, yes, yeah. They are called symmetric matrices because the elements are real. Hermitian is a generalization of symmetric matrices to include complex numbers. Yes, yeah, that's a good question, yeah. Okay, so your teacher is already warning me. So what we would do is we'll continue. Whenever there is a gap or some time in between, I'm generally here, so I'll try and fill it up. And if you need some time to sit down with me, and also who are my students? 3 of you are here, right? 1, 2, 3. So you will meet me after lunch, all 3 of you? Yeah, after lunch, after the extramural and lunch. My room is next door, 312, okay? I'll be in my room. Yeah, okay? Yeah, go ahead. I think you can.